I'm going to talk about diffraction through a single opening. But before I do, I want to do a review of double slit interference because the double slit interference ideas can be built upon to understand why you also have phenomena when light goes through a single aperture. So to review, when you have a double slit situation, and by the way, this can be made to three, four, five, seven, a million, a billion. You could take it out to infinity number slits. In fact, the double slit interference is the simplest example of a multi-slit interference, but you can actually have up to an infinite number of slits. And that is what's called a diffraction grating. And it turns out that the mathematics are the same. It comes down to light traveling slightly different distances by the time it hits the screen on the other side and talking about what that extra path length difference is in terms of the wavelength of the light. And so by screen, we've got some screen that when the light goes through the slits eventually hits the screen. And so the idea is that if you shine light and light goes through both openings, then the light is going to project onto the screen. So if you have light that goes through both openings and it has the same exact wavelength and they are in phase with each other when they go through both openings, then at the center of the screen, you have a isosceles triangle here. The distance from the top slit to the screen and the bottom slit to the screen are the same. And so there's no path length difference. So if the waves are in phase with each other, that means peaks align with peaks and troughs align with troughs. Then they're going to hit the screen still in phase with each other. And they're going to add up to make a super wave. And so you would have a bright region at the center of the screen. So you can imagine you'd have a bright region right in the middle. And this is called the central maximum. But you're going to have situations, I'll change color here, where you are going to think about a location somewhere else from the center. And so you can imagine now the two green paths, those paths are not the same distance. And more specifically, you can think of the difference in path length as this little piece that I'm scribbling in red right there. And that turns out to be d sine theta, where d is the distance between the two slits. And theta, so if you can just imagine you've got on one side your slits and on another side your screen, you can assume that the screen is relatively far away, especially given the size of the wavelength. And so if I draw a perpendicular line like this, then at some location on the screen, we are going to define some angle theta. And so that angle theta, if you think of like the position on the screen as y, like this distance right here is y, and you think of the distance from the slits to the screen as x, like this, then you can think of the tangent of theta, because with a right triangle, if theta is our angle, this would be our hypotenuse, this would be our opposite side, and this would be our adjacent side. And so the tangent of an angle is the opposite over the adjacent, which is the same thing as y over x. And again, theta is defined as this angle between where you have the openings and the angle swept either upper on the screen or lower on the screen from the central maximum, because you can also imagine that we can go below the central maxima. And so then that's how you have a relationship between the angle and how far away you are from the central maxima of the screen and how far away the slits are from the screen itself. And so the key, going back to d sine theta, is that when you have a difference in path length equal to an integer multiple of the wavelength, even though one wave travels further than the other, they're still in phase with each other when they hit the screen. And so you have another bright spot. And so when you have bright spots, M is going to equal 0, of course, that's the central maximum, but it can also equal plus or minus 1. It can equal plus or minus 2. It can equal plus or minus 3, and so on. And so if instead M is equal to plus or minus 1/2, plus or minus 3/2, plus or minus 5/2, and so on. Now the difference in path length is a half integer multiple. And so that means that that half integer multiple difference in path length results in the waves being out of phase with each other by the time they hit the screen. If they're out of phase, that means that peaks align with troughs and troughs align with peaks, and you have destructive interference and you have a dark region. And so when you think about the center of the screen, if you have light that goes through the slits and they are in the same phase when they go through the slits, then you're going to have a central maximum because it's equidistant path length that is traveled. But then you can think of alternating bright and dark spots. And so if you go up from the center of the screen, that's where you would use the pluses in the equations that I just showed. And so you would think of, for instance, the central maxima, but then you would have the first order or primary minima. That would correspond to when M equals plus 1/2. And then you can go on the bottom side as well. When M equals minus 1/2, you would have a primary minima. And then you would have a primary maxima. That's when you're dealing with plus or minus 1. Then you'll have a secondary minima. That's plus or minus 3/2. A secondary maxima, plus or minus 2. So you might get questions where you're asked to figure out like how far up on the screen or down on the screen you are for some order of maximum minima. And so just know that the order of the maximum minima just correspond to what the M value is. Just know that you're going to have a central primary maxima, and then that's going to have dark regions on each side of it, followed by bright regions, followed by dark regions, followed by bright regions. So just keep track of the M. Know that the pluses correspond to above the central maximum on the screen, and the minuses correspond to below the central maximum on the screen. The reason I review all this is because you can actually take a single slit, and you can think of that single slit as having these mini rays that have slight differences in path length as well. So what I'm going to do now is I'm going to draw a single aperture, and that single aperture is going to have a screen on the other side. And so imagine now that we have light shining on this single aperture. And what I'm going to do now, little d was the difference between your two openings. Or if you're doing a diffraction gradient, it's the difference between each opening. But now we just have a single opening. And so we are going to define that single opening as an uppercase D. So this time it's the width of the single aperture. Lowercase d is the width between the slits. Uppercase D is the width of the single aperture. And so now for simplicity, imagine, let's think of some spot on the screen, say right here. And let's think if we take the light and we break it into these mini waves, or sometimes they're called wavelets. So for simplicity, what I'm going to do is I'm going to draw 3 little mini wavelets. And so just like with the 2-slit example, you have a difference in path length here. And you also have a difference in path length here. And so it turns out that if the difference in path length between the top of the opening and the bottom of the opening is precisely one wavelength, then you can think of the ray coming right through the middle of the opening as having a path length difference of a half of a wavelength. So think about that now. Think of that light being broken into those three little mini wavelets. The top one is going to be a half wavelength difference in path length. Remember, if you have half integer multiple wavelengths, 1/2, 3/2, 5/2, that means you have destructive interference. That means you have a dark spot on the screen. So the top one and the middle one are going to cancel each other out when it hits the screen. And then also the middle one, which is, a half wavelength difference, and the bottom one, which is a wavelength difference in path length, they're going to cancel out because they're half an integer multiple wavelength different. And so you're going to have a dark region right here. And so it turns out that for a single slit, we are going to have the relationship for a dark region d sine theta. That should look familiar, but remember, the uppercase D now means the width of the single aperture. Lowercase d is the width between slits for either 2, 3, 4, or up to infinity number of slits. So it turns out that for the dark region, in the example I showed you, the path length difference between the top and the bottom when I broke the light into mini wavelets is going to be equal to m lambda, where m is going to be equal to plus or minus 1, plus or minus 2, plus or minus 3, and out to infinity. And so this would be your first order, second order, and third order, and so on, of minima or dark regions. And so for light regions, you're just going to have them in between. And so for light regions, you're going to have m equals 0, of course. That's going to be the central maxima. But then you're going to have plus or minus 3/2. That's between the 1 and the 2. Plus or minus 5/2. That's between the 2 and the 3, and so on. And again, the plus and minus just means whether you're above the central maxima of the screen or below it. And so you start with a primary in the center of the screen, and then you have first order, second order, third order, fourth order, and so on. That's how you think of the different orders of the bright and dark regions. So again, if you're asked a question where you need to figure out, like, where is like the second dark region? Well, you know that that corresponds to the second order minima, so it's either going to be +2 or -2, depending on whether or not you're above or below the center of the screen. And so I want to remind you just again that when you're talking about either interference or diffraction, it's the same concept. It's a concept of wave interference. It's the concept that waves, when they're in phase with each other, constructively interfere and make a bigger wave. When waves are out of phase with each other, they destructively interfere and they cancel each other out. And so when you have light going through openings and you have some screen that light eventually interferes to create an image, then you're talking about differences in path length that are being traveled based on what part of the screen you're on. And so sometimes the differences in path length correspond to integer multiples, which means that even though some parts of the light have to travel further, they're still in sync. Because remember, these waves repeat. They're periodic. And so even if they have to travel farther, if the amount they travel is precisely 1 wavelength or 2 wavelengths or 3 wavelengths or 4 wavelengths, they're still completely in phase with the parts of the light that had to travel less. And so if they're still in phase, they constructively interfere at the screen. The troughs add with the troughs, the valleys add with the valleys, and you have a bright region. But if the differences in path lengths are instead half integer multiple wavelengths, like a half of a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, in that case, now the waves are out of sync with each other. And now you have waves aligning with troughs, they cancel out, troughs aligning with, excuse me, peaks aligning with troughs, they cancel out, troughs aligning with peaks, they cancel out, and you have dark regions. So that's the name of the game. It's the interference of waves and thinking about whether the waves are in phase with each other or out of phase with each other. And the rest of it's geometry. So if you see a problem where you're dealing with light going through an aperture, ending up on a screen, you can think of the geometry of the distance between the slits and the screen. That's this X value that I drew up here. You can think of the distance on the screen as a Y. It's either going to be a positive or negative based on whether you're above the center or below the center. And you can use trigonometry to figure out what these different values are. You'll probably be given some and not others, and you have to do the trigonometry to solve the problem. But just remember that the other part of solving these kinds of problems is you're often going to be told to focus on, say, the first maxima or the third minima. And so that just comes down to these M values. And you're always going to have a primary maxima, whether it's multiple slits or single one. You're going to have a bright spot in the middle. And then you have your first order, second order, third order, and so forth. And that's what you see with the different values of M. So you can imagine, right, for, say, right here with the double slit, that's first order dark. This is second order dark. This is third order dark. All right. Now, when you're talking about a single slit, the diffraction through a single slit, then you're talking about, again, in the center, you're going to have a bright region, but this is first order dark. This is second order dark. This is third order dark. And one last thing, right? The plus and the minus. You're going to have a first order, second order, and third order dark, both above and below the center of the screen. So the plus corresponds to the above, the minus corresponds to the below. So turns out that when you have these apertures, you're going to have both interference and diffraction taking place. Because as you can imagine, if you have multiple slits, then you can think of it as this picture up here. But within each of those slits, you also have this picture right here. And so it turns out that both of these phenomena are taking place when light interferes and casts images on a screen. But that being said, there's a common theme. And the common theme is that there's going to be slight differences in path length. And those slight differences in path length are going to result in constructive interference if the differences in path length are integer multiples of a wavelength. And when you talk about the differences in path length having half integer multiples, that's when you're talking about destructive interference. And so constructive interference, again, that's integer multiple wavelength path differences. That means bright spots. If you're talking about half integer multiple wavelength differences in path lengths, you're talking about destructive interference, and that means you're talking about dark spots. But all of this comes down to the principle that waves in phase with each other add up to a super wave. Waves out of phase with each other cancel each other out.